y'all, Barry Berry Jr. back for some more physics. So we left off earlier today here where we were looking at some circular motion, and we'll continue with it for uniform circular motion. And I left off at the problem with the proton circling and picked up a new meaning of omega. So perhaps I should look at that a bit more and actually go through the proton problem and make sure I have that worked out. So angular frequency is how, the time change at which the angle is changing. So let's see what we have. Circular motion of a proton. For example, 411. So a proton, it says speed equals 5×10⁶ meters per second, moving in a circle. The radius is 0.175 meters. What is its position in the XY plane at t equals 2.0 times 10⁻⁷ seconds. And we have aura of t equals 0 equals 0.175 meters I. So it's right, we identify the starting position as the x-axis. We can determine our coordinate system however we like. And the proton is moving that way around the center. So that equation is necessary to figure out the period and thus the angular frequency. So let's go back to that equation again on the formula sheet and get used to rederiving it. I believe we'll have this formula sheet. Well, this class, this foundations class will have classical mechanics, quantum mechanics, and I believe EM. So understanding is whenever we're doing classical, we'll have this formula sheet. So that formula, as it is on the sheet, is centripetal acceleration equals the tangential velocity squared divided by r, which equals r times the angular frequency squared, how much the angle changes per second squared. So what we did earlier, we took these two and we said v squared over r squared equals omega squared. Slightly different order, but same thing. So then we can say the angular frequency equals the tangential velocity divided by the radius. And it gave us the radius and it gave us the tangential velocity. Thus, the angular frequency of the proton equals the angular velocity divided by the radius of the proton. So that's going to be 5 times 10⁶ meters per second divided by 0.175 meters. And they did the match for us already. Actually, they did it slightly differently. But let's plug it in this way and see if we get the same answer. So I do get 2.857 E7, and this is going to be radians per second. So that matches. And the period equals 2 pi over the angular frequency, which equals 2 pi divided by 2.857 E7 radians per second. So that equals 2 pi divided by the previous answer. So I get 2.2 times 10 to the negative 7 seconds, because it's radians divided by radians. So I should say 2 pi radians. All right, so that matches. The position of the particle, we want the position in the XY plane at that time. Let's see what they're doing here. Take cosine, put that in. Interesting. So this equation that we used earlier, or that we derived earlier, is useful again. Let me see if this is on the formula sheet. So looking at it, that is not on the formula sheet. So I guess that's just something to remember. You have to remember that is radians per second. Therefore, omega t equals radians equals theta. And r t equals r cosine theta I plus r sine theta j equals r cosine omega t I plus r sine omega t j. So what they're saying is that r at t equals two to put this here. equal to e negative 7 seconds equals 0.175 meters cosine 2.857 E7 radians per second times 2 negative 7 seconds I plus 0.175 meters sine 2.857 E7 radian per second times 2e7 sec 2e to the negative 7 seconds j. So that equals 0.175 cosine 2.857 E7 times 2e to the negative 7. So that's 1.74 e to the negative 1 pi. Oh, 4-7. I mean, you have 7-4, they have 4-7. Maybe I typed something wrong, but the idea is the same. We'll keep it rocking. And it's the same thing, except sign for this one. Right, so I must have typed something wrong. Let's take a look and see. Cosine 2. Typed everything in right. 7.5 cosine 2 to the 7 times 2. 7.5 times 2. When we're dealing with radians, we have to use degrees. You see me out dealing with radians, we can't use degrees. I have to remember that. Radians in calculator. So some of these problems have degrees, others have radians. Perhaps it's best to just always use radians. All right, I got the same thing. Can't be right. Oh, no, I did get something different. All right, there we go. That's what it is. That's why it looks strange. It swapped the sine and cosine values when I started using radians. That's interesting. So in other words, when I had that amount of degrees, the cosine value is the sine value when I use radians. That's because the number is so small, maybe it's approximation. But when I use radians instead of degrees, I get the answers they got. 0.147 I minus 0.094. That's the position it's at when those amount of seconds have passed, when it has that amount of tangential velocity. And it'll put it over here somewhere. All right. So that detail may help me with the problem. Oh, and look. She drew it out for us. Take the initial position of the particle to be the x-axis. This is completely arbitrary. For different starting position we're given, we will have a different final position at t uh, uh, 200 nanoseconds, but of course the amount of distance it would have traveled and the angle it would have traveled through would be the same. So let me take a look at my problem now. I'll see if I have enough to solve it at this point, because this is going into non-uniform circular motion, and I'm pretty sure the problem was uniform circular motion. So let me take a look and see. Need some more time with the okay, here we go. What do they say non-uniform though? Let's see what they're talking about, because I do say that we're getting the acceleration or something going around in a circle. So let's see what they say. It says non-uniform circular motion. Circular motion does not have to be at a constant speed. The particle can travel in a circle and speed up or slow down, showing an acceleration in the direction of motion. In uniform circular motion, a particle executing circular motion has a constant speed and the circle is a fixed radius. If the speed of the particle is changing as well, it will introduce an additional acceleration in a direction tangent to the circle. Such accelerations occur at a point on the top. Such accelerations occur at a point on the top that is changing its spin rate. For any accelerating motor. In displacement and velocity vectors, we showed that centripetal acceleration is the same as the time rate of change in the direction of the velocity vector. If the speed of the particle is changing, then it has tangential acceleration. That is the time rate of change of the magnitude of the velocity. Hmm. The direction of tangential acceleration is tangent to the circle, whereas the direction of centripetal acceleration is radially inward towards the center of the circle. Thus, a particle in circular motion with a tangential acceleration has a total acceleration that is the vector sum of the centripetal and tangential accelerations. Right? That makes sense. So we have A T equals dv over dt. And we have A total equals AC plus AC. Let me check that problem out and see if this might help. The maximum speed, minimum speed. Not exactly. So if I can find I expected to find yes, I think this is more of what we need. There we go. It's about coefficient of frictions when things are moving. Okay, let's go through applications of Newton's laws. So I'll go ahead and change the text and everything. Right, so we're going to talk about some applications of Newton's laws. Correlation on the grand P, called speeds of 200 miles per hour. Right, so this is exactly what we need: friction centripetal force. Introduction. Car racing has grown in popularity in recent years as each car moves in a curved path around the turn. Its wheels also spin rapidly. The wheels complete many revolutions while the car makes only part of one, a circular arc. How, when we describe the velocities, accelerations, and forces involved, what force keeps the race car from spinning out, hitting the wall bordering the track? Who provides this force? Why is the track banked? We answer all of these questions in this chapter as we expand our consideration of Newton's laws of motion. Right? So it says by the end of this section, we'll be able to apply problem-solving techniques to solve for quantities in more complex system of forces. Need that. Use concepts from kinematics to solve problems using Newton's laws of motion. Solving more complex equilibrium problems. Need that. Solve more complex acceleration problems. Need that. Apply calculus to more advanced dynamics problems. We don't need to do that, but at least not on this exam, but we'll see. Success in problem solving is necessary to understand and apply physical principles. We developed a pattern of analyzing and setting up the solutions to problems involving Newton's laws and Newton's laws of motion. In this chapter, we continue to discuss these strategies and apply a step-by-step process, problem-solving strategies. We follow here the basics of problem solving presented earlier in the text, but we emphasize specific strategies that are useful when applying Newton's laws of motion. Once you identify the physical principles involved in a problem and determine that they include Newton's laws of motion, you can apply these steps to find a solution. These techniques also reinforce concepts that are useful in many other areas of physics. Many problem-solving strategies are stated outright in the worked examples, so the following techniques should reinforce skills you've already begun to develop. So let's see what we have here. 1. Identify the physical principles involved by listing the givens and a quantity to be calculated. Find the physical principles. Givens, quantities, and unknowns. Guess the simulation using arrows to represent all forces. So we'll just say free body diagram. Determine the system of interest. The result is a free body diagram that is essential to solving the problem. So that seems to be one step to me. 3. Apply Newton's second law to solve a problem. F equals ma. If necessary, apply appropriate kinematic equations from the chapter on motion along the straight line. And kinematics. Check the solution to see whether it is reasonable. Let's apply this problem-solving strategy to the challenge of lifting a grand piano into a second-story apartment. Once we have determined that Newton's laws of motion are involved, the problem involves forces. It involves Newton's law of motion. any force problem. It is particularly important to draw a careful sketch of the situation. Such a sketch is shown in figure 6.2a. Then, as in figure 6.2b, we can represent all forces with arrows. Whenever sufficient information exists, it is best to label these arrows carefully and make the length and direction of each correspond to a represented force. By taking another level by taking into account the length of the arrows. So we have the sketch. We identify the forces. Define the system of interest. Force. This force is not a force on the system of interest, but rather a force exerted by the system on the outside world. It must be omitted from the free body diagram. I guess they're saying that this is the weight pulling down the crane. Free body diagram. The tension and the weight balances. These forces must be equal and opposite since the net external force is 0. Thus T equals negative W. So then we add up the forces. The grand piano is being lifted to a second-story apartment. Arrows are used to represent all forces. T is the tension in the rope above the piano. Ft is the force that the piano exerts on the rope. And W is the weight of the piano. All other forces, such as the nudge of a breeze, are assumed to be negligible. Suppose we are given the piano's mass and asked to find the tension on the rope. We then define the system of interest as shown and draw a free body diagram. Now Ft is no longer shown because it is not a force acting on the system of interest, rather Ft acts on the world outside, pulling the crane down. Showing only the arrows, the head to toe method of addition is used. T plus W equals 0 if it's not, floating up towards the crane or falling away from the crane. They equal and opposite. And then to set them equal and opposite. That's what most problems we next need to identify what needs to be determined and what is known or can be inferred from the problem as stated, that is, make a list of knowns and unknowns. It is particularly crucial to identify the system of interest, since Newton's second law involves only external forces. We can then determine which forces are external and which are internal, a necessary step to employ Newton's second law. Newton's third law may be used to identify whether forces are exerted between components of a system internal, or between a system and something outside external. As illustrated in Newton's laws of motion, the system of interest depends on the question we need to answer. Only forces are shown in free body diagrams, not accelerations or velocity. We have drawn several free body diagrams in previous worked examples. 6.2c shows a free body diagram for the system in interest. Note that no internal forces are shown in a free body diagram. And I guess the internal forces would be the crane pulling up the piano and the piano pulling down the crane. Free body diagram is just drawn. We apply Newton's second law. This is done in figure 6.2d for a particular situation. In general, once external forces are clearly identified in free body diagrams as to be external forces, it should be a straightforward task to put them into equation form and solve for the unknowns as done in all previous examples. If the problem is one-dimensional, that is, if all forces are parallel, then the force system can be handled algebraically. If the problem is two-dimensional, then it must be broken down into a pair of one-dimensional problems. We do this by projecting the force vectors into a set of axes chosen for convenience. As seen in previous examples, the choice of axes can simplify the problem. For example, when an incline is involved, a set of axes with one axis parallel to the incline and one perpendicular to it is most convenient. And let me see if I did that on my exam on one of these problems. So I think that might be what got me. Oh, no, I did. They break it up into fx and fy. Right, so I'll see what I did incorrectly. It is almost always convenient to make one axis parallel to the direction of motion if this is known. Generally, just write Newton's second law components along the different directions. You have the following equations: fx equals max, fy equals may. If, for example, the system is accelerating horizontally, then you can just set ay equals 0. We need this information to determine unknown forces acting on the system. All right? As always, we must check the solution. In some cases, it is easy to tell whether the solution is reasonable. For example, it is reasonable to find that friction causes an object to slide down an incline more slowly than when no friction exists. In practice, intuition develops gradually through problem solving. With experience, it becomes progressively easier to judge whether an answer is reasonable. Another way to check a solution is to check the units. If we are solving for force and end up with units of millimeters per second, then we have made a mistake. There are many interesting applications of Newton's laws of motion, a few more of which are presented in this section. He served also to illustrate some further subtleties of physics and to help build problem-solving skills. We look first at problems involving particle equilibrium, which make use of Newton's first law, and then consider particle acceleration, which involves Newton's second law. Right, so particle equilibrium is Newton's first law. Acceleration. So I may come back tonight and actually work these examples here. Like that with machine. Helicopter, tractor, vertical projectile, friction. All right. section. Triple force. Keeping the car from slipping. Bank curves. So these are definitely what we need to do. These bank curve ones. So I'll come back tonight. I think we shall start here with centripetal force. This is most directly related to the problem. Right here. All right, so we'll come back tonight and I'll start with 6.3 and for the normal show. And we will take a look at some centripetal force. And I'll see if I can solve the related problem. So, like, subscribe if you haven't already. Help me get to 1,000 subscribers. I'll be back tonight at 8 p.m. Central Time, and we'll look at some problem solving. I'll set up a problem solving video, and we'll go through these examples. I'll see y'all later.